Welcome to The Explainer. Today, we're tackling a concept that sounds like straight-up sci-fi, but is actually an urgent multi-billion-dollar reality: building AI data centers in space. You know all about the AI boom, right? But the hidden cost nobody talks about is the absolutely massive amount of electricity it takes to run these models. Earth's power grids are literally tapped out, so tech giants, they're looking up. They're looking to the stars for a solution. Okay, let's dive into this.
To really get why anyone would even consider stacking servers to a rocket just to generate AI faster, you have to look at this number right here, 100,000. That is roughly the number of homes that consume the exact same amount of electricity as just one single large AI data center down here on Earth. Just one. Now, multiply that by the hundreds of new facilities that hyperscale tech companies are furiously trying to build right this second. It's wild. We aren't just talking about a mild strain on the grid here. We're talking about a fundamental collision between the relentless growth of AI and the physical limits of our planet. Land, water, electricity, we're maxing it all out.
Now, what's really interesting about this is how tech companies are hitting a massive brick wall down here on the ground. By 2030, US data centers alone are on track for a 130% jump in electricity demand. Globally, data centers could soon devour 8 to 10% of all the power consumed on Earth. But it's not just about generating the power, it's about time. If you want to build a new facility in major tech hubs, think Northern Virginia, California, parts of Germany, you are looking at a 7 to 12-year delay just to get connected to the electrical grid. 7 to 12 years. Even with tech giants planning to drop a staggering $400 billion in a single year on ground-based centers, they simply can't build them fast enough. So why space? Well, the physics of low Earth orbit make it incredibly attractive. Down here on Earth, even on a perfectly clear day, your typical ground-based solar panels are only capturing about 150 to 300 watts of usable power per square meter. Our atmosphere scatters the light, clouds get in the way, and, well, the sun sets every night. But up in low Earth orbit, it's a totally different ballgame. A satellite placed in a dawn-dusk sun-synchronous orbit gets blasted with roughly 1361 watts per square meter. There's no atmosphere blocking the light. There is no weather. And the absolute best part? They can sit in direct, completely unfiltered sunlight for up to 99% of the year. It's raw, uninterrupted, limitless power.
And listen, we aren't just talking about slapping some standard rooftop solar panels onto a satellite. 2026 era space-grade solar cells are hitting an unbelievable 40 to 50% energy conversion efficiency. That completely blows typical commercial silicon panels out of the water. When you combine that extreme efficiency with the constant, intense sunlight of low Earth orbit, it means a solar array in space can generate a dramatically higher amount of usable energy per square meter than that exact same physical array ever could on the ground. I mean, it's a total engineering game changer.
So, who's actually pulling this off? Right now, two heavyweights are leading the charge. You've got SpaceX and xAI actively discussing space as potentially the lowest cost location for AI compute in the near future, and they're planning to leverage their massive Starlink-class launch capacity to do it. Meanwhile, Google isn't just sitting around theorizing. Their Project Suncatcher is already partnering with Earth observation satellite makers like Planet Labs, and they're actively testing their own specialized radiation-hardened TPU chips, that's tensor processing units, specifically designed to run in orbit. The biggest players on Earth are literally racing to claim the skies.
But hey, it's not just the legacy tech giants throwing their hats into the ring here. Take Etherflux, founded by a co-founder of Robinhood. They've already raised around $50 million. Their vision is twofold: beam power down from orbit, sure, but also run AI workloads directly on those exact same satellites. This is a huge signal. It shows that serious venture capital is flowing into the space, proving this isn't just some sci-fi pet project for billionaires. It's a rapidly maturing sector with aggressive, well-funded newcomers ready to disrupt the whole shebang. Then you have Meta taking a slightly different approach, though it's equally ambitious. Back in April 2026, Meta and Overview Energy inked an agreement aiming to capture up to 1 gigawatt of space-collected solar power. But here's the twist. They aren't computing in space. Instead, they plan to use near-infrared lasers to beam all that collected solar energy straight down to existing terrestrial solar farms, giving them a massive boost during peak demand hours or at night. They're actually targeting an orbital demonstration by 2028, aiming for commercial delivery by 2030.
And this brilliantly illustrates two diverging philosophies happening right now in this new industry.
On one side, you have the beam the power down camp, like Meta. They want to solve the energy crisis on Earth by sending space power back home. But here's the catch. Transmitting power through the atmosphere means you lose a significant amount of energy along the way. Then you have the keep the compute up camp, SpaceX, Google, StarCloud, Aetherflux. This is widely considered the more transformative, though definitely more difficult path. By placing the actual AI processors right next to the solar panels in orbit, you avoid those transmission losses completely. The power is generated and consumed in the exact same spot. But keeping the compute up in orbit introduces a massive, deeply ironic engineering challenge. You might be thinking, hey, space is freezing cold, so cooling servers should be a breeze, right? Well, actually, no. Space has no air. Here on Earth, we rely on air, water, and chilled liquids to carry heat away from densely packed AI chips using convection. But in the vacuum of space, convection doesn't exist. The only way to get rid of the immense heat generated by these AI chips is to move it through the spacecraft and radiate it away as infrared energy. To pull that off, you need massive radiators, which can honestly end up being as big or even bigger than the solar rays themselves. And honestly, heat is just the beginning. Surviving the vacuum of space means running a brutal physical gauntlet. Beyond radiating all that heat, you've got cosmic radiation, which can literally corrupt your data and degrade transistors over time. That's exactly why companies like Google have to design those specialized radiation-hardened chips. Then you have to somehow dodge orbital debris in an increasingly crowded low Earth orbit. But the absolute most daunting hurdle? Maintenance. You can't exactly send an IT guy in a van up to low Earth orbit. If a server breaks up there, it stays broken. So the hardware reliability standards have to be absolutely flawless from day one.
But let's say you solve all the physics. You still run straight into a massive logistics bottleneck: rockets. Getting this whole system to work requires moving astronomical amounts of data back to Earth and also between the satellites themselves. Now, Google has successfully tested optical intersatellite links in the lab at blistering speeds of 1.6 terabits per second, which is amazing. But the bigger issue is actually launch capacity. Just to deploy 100 megawatts of orbital compute capacity, you would need 50 or more dedicated rocket launches. Right now, even the most advanced reusable rockets are launching at a fraction of the cadence needed to pull off a build-out of that magnitude. Rocket availability is, without a doubt, the biggest choke point for this entire industry. Let's move to and see how this builds a realistic picture of the near future. Look, most analysts don't expect space data centers to just completely replace our terrestrial ones anytime soon. Instead, they're going to dominate these highly specific, really high-value niches. First off, processing data generated in space, think satellite imagery, right there in orbit without having to beam all that heavy raw data down first. Second, ultra-secure workloads that actually benefit from being physically cut off from terrestrial networks. Third, applications that desperately need low-latency global reach. And finally, handling those heavy, non-time-sensitive AI training workloads that can tolerate the current orbital limitations, which frees up crucial ground-based capacity for faster, more urgent tasks. And the timeline for all this is moving incredibly fast. In early 2026, we saw these mega constellation filings hit the FCC, proposing over 1 million satellites combined. Fast forward to mid-2026, and Google is already demonstrating 1.6 terabit per second laser links and testing hardware in orbit. But mid-2026 is also when reality hits hard. Rocket launch cadence is severely lagging behind demand. The true turning point, the moment everything changes, sits at the end of this timeline. Analysts project that by the mid to late 2030s, launch costs could plummet below $200 per kilogram. That right there is the magic number. When launches get that cheap, orbital data centers shift from being a cool niche experiment to broadly economical everyday infrastructure. So the crucial point is the money. Industry analysts estimate that the orbital data center market will sit at around $1.77 billion by